Hello, it's Mr. Norris. The purpose of this video is going to be to talk through some exponent rules to add on to the exponent rules that we've already learned. So let's just very quickly review those. We've learned that you can have exponents other than simply positive integer exponents. So you may know how to do something like 3 to the second power, and that's been something you've been doing for a long time. It just tells you to do 3 times 3 and it gets you to 9. But now you can think about stuff like 3 to the negative second power, and you know how to deal with those situations where you would do 1 over 3 to the positive 2 and get 1 over 9. So if we're going to really be generalizing what we're doing here, we have a example here, but let's try and make it just into somewhat of a general rule. So we learned that if you have some constant raised to the negative n, you can write that as 1 over that constant to the positive n. Okay, so we have that. We also learned that there is a relationship between radicals and fractional exponents. For example, if I have 16 to the 1/4, that's going to be the same as the 4th root of 16. More broadly, if I have something like 16 to the 2/5, that's going to be the same thing as the 5th root of 16 squared. So that general rule looked like a some constant to the m over n, and we were able to set that equal to the nth root of a to the m. So we're going to combine some of these ideas such that we can work with more complicated and more interesting expressions. So far you've only thought about the effect of some exponent on a single base. But what if you have an expression with multiple bases and multiple terms and you're trying to simplify that? That's really going to be our purpose here. So let's consider something like x to the 5th times maybe x squared. So if we're going to write that out, what that's actually saying is this. We have x times itself 5 times, so x times x times x times x times x. And then we're going to multiply that out by x squared, so that's x 2 times, x times x. Okay, so that comes out to x to the 7th because there are 1, 2, 3, 4, 5, 6, 7 terms. So this is going to come out to x to the 7th. So what do you notice about our original problem, x to the 5th times x squared, and our final answer, x to the 7th? Think about that for a second. So I have x to the 5th, and I have x to the 2nd power, and I got x to the 7th. So really what happened is I had a 5 here and a 2 there, and perhaps those were somehow added together, and I got to x to the 7th. In reality, that's what's happening when you multiply two terms by the same base. Two terms that have different exponents but the same base. So our general rule for this circumstance is as follows. So if I have the same base a, and I raise it to the m power, times the same base a, and I raise it to the n power, then all that I have to do when I'm multiplying is write one term, but then add the exponents. So, not too bad. We're going to take that, and we're going to set it off to the side for a second, and we're going to consider the same problem, only division. I want you to think about something like x to the 5th, and let's say divided by x to the 7th. Oops, didn't mean to do that. Here we go again. X to the 5th over x to the 2nd. So what's happening is we have 5 x's on the top again, and then we have 2 x's on the bottom. So what's going to happen is we're going to have 2 of those x's cancel, and we're going to be left with 3 x's, x times x times x. And we know that that's equal to x to the 3rd. So what's the relationship between our original problem and our final answer? Well, we have a 5 here and a 2 there. We got to a 3. So this is actually a situation where we're subtracting exponents. So our general rule is going to be this. Take this and set it off over to the side. Maybe zoom it out just a little bit. Okay, our general rule is going to be that when we have some letter a to the m over some letter a, some constant a to the n, that's the same as a to the m minus n. So we see some similarities between when we are multiplying two values with the same base and when we are dividing by two values with the same base. This rule and this rule are going to be very important, and it's going to be something that you're going to have to use over and over. In our next slide, we'll look at some more examples. In our next example, let's consider x to the fifth power times x to the negative third all over x to the negative fourth times z squared. Okay, so we got a lot of interesting things going on. So first of all, we have two terms in our numerator and two terms in our denominator, and we're going to have to find a way to simplify this. So let's simplify the top part first. So I see that I have a common base, x and x, and I'm multiplying, so that means that I can add my exponents. I have 5 plus negative 3. That gets me x squared. And then I'm just going to rewrite my denominator. So I have z squared times x to the negative fourth. So you might be tempted to do something like, let's say, z to the negative 2, because you might want to add 2 and negative 4 and get negative 2. Or you might be tempted to mark that out and say something like x to the negative 2. But in reality, we cannot do either. Z squared or z and x are not the same variable. So what I would actually recommend doing in this case is go ahead and rewrite what you have in the base, and then since you have two separate variables, go ahead and separate out this single fraction into two fractions. So let's do that. So now I'm going to have one fraction here. I'm going to have my x squared on the top, and I'm going to put my x to the negative fourth on the bottom. So I have one fraction with all of my x's. Then I'm going to write another fraction with all of my other variables. So do I have any z's in the top part of this new fraction? Nope. I have no z's there because there are no z's up here. Do I have any z's in the bottom part of my fraction, in my denominator? Well, yeah, I have z squared. So I'm going to go ahead and write that in here as well. Alright, looking good. So now we've taken one fraction and made it into two fractions. I'm going to take all this and resize it a bit, put it off to the side, and we're going to keep going. So now, let's think about how we would simplify both of these individually. So, in this example, I simply have, or excuse me, in this particular fraction, I have a situation where I can subtract my exponents. So I'm asking myself, what is 2 minus negative 4? So 2 take away negative 4 is actually x to the positive sixth. Okay? And then 1 over z squared, well, I know I could write that if I wanted to as z to the negative second. And so I've taken a really, really complicated expression, and I've employed some rules that I've learned to be able to take a complicated expression and go through some steps and get to a far more simplistic and easier to read expression. Okay, so the key here, first of all, is before you start working up and down, before you start thinking about how to combine your numerator and denominator, try and view the numerator by itself first, then view the denominator by itself. Once you've done that, see if you can take one fraction and split it into multiple fractions, depending upon the number of variables that you have. So you want to get a situation where you have one fraction with multiple variables to a situation where you have multiple fractions, each that have the same variable. And after that, you're in a case where you can employ the exponent rules that we learned in the original video on exponent rules. We'll look at one more example in our next slide. So for our final example, we're going to look at a relatively complicated expression. The main difference from this expression to the last expression, well, first of all, you're dealing with a lot of exponents that contain fractions, and you're also dealing with a exponent on the outside of the entire term. So we're unaccustomed to seeing a fraction raised to some exponent. So I think the first thing that I'm going to do is try and simplify everything that I can inside the parentheses before dealing with this outside exponent. Maybe I'll make this easier by going ahead and splitting this into 3 different terms. So first, I'm going to write out my constant. So I have 16 to the 3/2. And then I'm going to think about my x terms. So x to the 1/6 over x to the negative 1/6. And all that is still to the 3/2 power. And then finally, I'm going to have my y terms, where I have y to the negative 2 over y to the 6th. And I'm also going to raise that to the 3/2. So maybe now that I have all of these separated, I'm going to see if I can go ahead and get rid of these 3/2, because they're kind of annoying me a bit. So now I'm going to try and take the square root of 16 to the 3rd power. So I employed a rule from here to here, where I can take some base to a fractional exponent and convert it into a radical. Okay? And now I'm going to consider what happens from here to here. So when I have a exponent on the outside of another exponent, in this case 2 terms with the same base, fractional exponents on the inside, there's this question of what I do with this thing and these 2 terms on the inside of the parentheses. So the idea is that you want to be able to take this exponent and multiply it times the exponents in here. So first off, let's think about x to the 1/6, and then let's think about that 3/2. So what I'm really doing is I'm taking x to the 1/6 times 3/2. So that becomes x to the 3 for 3 times 1, and then over 6 times 2, which is going to be 12. So x to the 3 over 12. And same thing on the bottom, x to the negative 3 over 12. Okay, let's consider that additional problem. So we have y to the negative 2 over y to the 6. We're going to do that same task where we take something on the outside and multiply it by the exponents on the inside. So let's have this as y to the negative 6 over 2 all over y to the 18 over 2. Okay, we'll close parentheses here, and we will zoom out just a little bit. So we're going to take all of this, push it over to the side. Okay, so let's go term by term again. Let's take this radical and try and split it up a bit. So we have the second root of 16 times 16 times 16. And then I know in this next term that I can subtract my exponent. So I have x to the 3/12 over x to the negative 3/12. So what is 3/12 take away negative 3/12? That gets me to x to the 6 over 12. Okay, and then I get y to the negative 6 over 2 over y to the 18 over 2. So negative 6 minus 18 is the same as y to the 24 over 2. Excuse me, negative 24 over 2. Okay, we'll close parentheses there, and we will keep simplifying a bit. So let's take all this, zoom out one more time. So the square root of 16 times 16 times 16. Well, really what we have there is the square root of 16 squared, which is 16 itself, and then times one more square root of 16, which is 4. Okay, then we have x to the 6 over 12, which is the same as x to the 1/2. And then y to the negative 24 over 2 is the same thing as y to the 12th. So let's go ahead and write that in as y to the negative 12th. Okay, we'll just have one more simplification. So 6 times 4 clearly gets us to 64. X to the negative 1/2 can be written as the square root of x. And y to the 12th, to the negative 12th, can be converted into a fraction, which can be 1 over y to the positive 12th. So we took a really complicated expression at the top, and we were able to get it to 64 times square root of x over y to the 12th. So this can show us how powerful these rules can be when we combine them to take a complicated expression and turn it into something simplistic.